Ready?
By the way, Ben, congratulations. Ben got engaged and he's getting married in 3 months. Ben, Mazel Tov to you.
Thank you. Thank you.
Mazal tov.
Okay. So hello, everyone. I feel like Frank Sinatra with his microphone, like I'm a singer. So my name is Ben, and I'm an electromechanical engineer here at Innovation Africa. And I will talk to you about the electricity and water project guide. I will walk with you with all the electrical aspect in a water project. So you will be knowledgeable of everything. Note that just like Sivan mentioned, we have another in-depth presentations in Thursday. So don't panic if you don't know everything. You'll have another presentation and you also can ask anything you want. So everything will be clear. Okay, so the agenda for today is we're going to view, just like I said, the electrical engineer responsibility in a water project. And I'm going to show you all the technologies we use in a water project. This is a wonderful electrical engineering team in Israel. We have the famous celebrity Meir Yacobi, our chief engineer. We have Jeremy, the hacker, the software engineer. And you have Sagit, any one of you who's involved with the monitoring unit installation, know the great Sagit. This is our Uganda team, Dennis and Eric. Malawi, Robert and Moses with the great joke. We have South Africa, Rudzani, Karabo, Amfo, Valencia. Zambia, Yazenga and Murfin, and Cameroon, Yanawa Bidai. So this is the steps we expect of all electrical engineers to be involved in all water projects. The first two steps are in the design process, and the next following steps are already installation. So we review the installation and make sure everything is according to plans. So the first step, just like Emily and Shai mentioned in their lectures, we're gonna first walk about the pumping test results and depth of the pump and everything with the hydrology aspect. And then the water engineer gonna choose the EPANET design and total dynamic head. They're gonna suggest the pump. And then the electrical engineer walks in and review and approve the solar pump and chooses the controller, floating switch, solar panels. We're gonna walk you through everything. Here you can see the process, just like I mentioned. We got the hydrologist, we got the pumping test results, we have the depth of the pump and all the data. And then the water engineer takes the data, analyze it, plan the EPANET design, calculate the total dynamic head, and suggest the pump. And then we walk through and we see the suggestion that we got from the water engineer. And then we see if we approve it. Why we need to approve it? Because a pump has the water aspect and the electrical aspect. So we need to check that it's according to plans and fit the solar panels and controller and quantity to the following pump we choose. Now, just like Sivan mentioned and everyone mentioned, we have a new standard, which is 1 liter per second standard, which is 3,600 liters per hour, 3.6 scoop per hour. That this is the yield rate we wish to have in every borehole. Therefore, we need to choose a pump that will deliver us the same flow rate. So the data we have is the desired flow rate, the yield, and the total dynamic head, which Shai explained us wonderfully in her presentation. Then we take the two parameters and we go to Grundfos pumps, the Grundfos website, and then we have a wonderful tool I'm going to walk you through to see how we select the pump according to the data we have from the water engineers. Now, Grundfos has 90% of our projects, and we wish to use it in the most of our projects as well, except extraordinary projects. So Grundfos has two families of pumps. The first one is the SQ Flex pump, and the second is the SP pump. Now, as you may know, most of you, the solar panels gives us direct current from the sun. It gets a DC, and most of the electric consumers, such as pumps, uses alternate current, AC. So what Grundfos made, they made a wonderful pump called SQ Flex that makes our life easier for organizations like Innovation Africa. It uses the power from the sun to power pumps and get water. And they made a pump with an internal inverter inside, so we can give direct current from the sun. And then inside the pump, we don't need an extra inverter outside, an extra components, and it directly converts the electricity from DC to AC, which saves us money and complicity. That's why we rather use the SQ Flex pumps in all of our projects if we can. It has an internal inverter. In some of the projects, we can't use the AC pumps. We can't use the DC pumps, sorry. And that's why we're going to use the SP pumps, which is AC, and they need an extra inverter outside. It gives us more power, and therefore we get a higher flow rate for a higher TDH projects. I remind you the total dynamic head, TDH, it's the length, a distance we have from the water to be pumped outside.
So just to repeat, Ben, what you're
Yes.
trying to say, that oftentimes we should always try to use DC pumps, direct current pump, that we can use the energy from the solar panels directly in order to power the pump, DC pumps. Because if we're using AC pumps, we need to add an inverter, and oftentimes we need more solar panels. But you also said that sometimes we cannot find DC pumps for larger projects. And therefore, sometimes we do have to go with bigger pump, and most of them are AC. And I'm sure you're going to show us the difference in a moment.
Yes, I'm going to show you everything. Just like Sivan said, here we made your life easier, and we made you a list of the pumps we prefer to use. So just like Sivan said, we rather use DC solar pumps. This is the first lesson. Always try to select a DC pump first if it answers the requirements. Now, I'm sure that all of you involved in water projects know that a lot of our projects uses SQ Flex 2.52. But because of the new standard we have, that it's 3.6 coup per hour, the minimum pump we will use is SQ Flex 3. Why? Because the SQ Flex 2.5, the maximum flow rate is 3, and we need more than 3. We need a minimum of 3.6, 1 liter per second. Now here you can see the first pump in the list. It's SQ Flex 3810, which gives us 3 to 5 coup per hour. We're going to walk you with the pump curve, and I'm going to show you everything so you'll understand. And then if we have a higher TDH, a higher TDH project, we're going to choose the SQ Flex 5870. And then if we have a higher TDH, we're going to use the 3105. And I'm going to show you again the pump curve. And then if we have a higher flow rate in the project, let's say we have to use 2 towers and we have a higher flow rate and higher TDH, we're going to use the AC pump. The first 3, that's right preferable, don't need an extra inverter and don't need extra solar panels. I'm going to explain more and elaborate in the future. So this is a common pump curve. This is the first pump I talked about, the 3810. As you can see on the left, it's the Q. This is the flow rate, coup per hour. The curves are the TDH, as you can see, 30, 35, 40, 45. And in the bottom, we have the power we need to put in the solar panels in order to power the pump. You can see the red line, which is the IA minimum standard of 3,600 liters per hour. So in this specific pump, if the TDH is higher than 60, we can't use it because it's lower than 3.6. This is the next pump, the SQ Flex pump. Here you can see we get a higher flow rate and a higher TDH. And also we need more solar panels, but it's okay. So let's say we have 3.6, you can see that we can get TDH of 100 meters, which is a lot. You can see the next curve, the next pump. You can see the AC pump, the first one. You can see we can put a higher flow rate in a higher TDH, 120, 25, and the next one. Now, this is Grundfos' website. I'm going to walk you through, in general, how we choose a pump. First, you need to sign in order for it to save your data, and we want it. And then we go to products and services. And then we can choose our specific application. It's very important for us to choose the municipal water supply and solar water solutions and solar systems, because we have situations that we got proposals for a pump that didn't suit the solar system. So it's very important for us to write it's a solar system in order for us to get the pumps that uses only solar and DC, and we don't need extra components we don't really need. Now, the thing is, the more data we will insert the website, the more precise the system will be. So we can put the location inside, so it will know the radiation of the sun. And we can put, of course, the water volume, the flow rate. You can see that I multiplied it by 6 because you need to put it cube per day. And 6 is the number, is the commonly used for sun radiation. If you know that your country is different, you can also rely on our monitoring system. You can select differently, but please ask us and advise why you do it before. Here you can see the static lift and dynamic water level. Just like Shai said, the sum of the static lift, dynamic water, and the pipe system friction loss, the head, will be the total dynamic head. And we choose January, it's the worst month, because we want to be more strict. And we know that January has less radiation. And that's why we will choose this, because we want to be prepared for the worst situations. Yes, Ivan?
Yes, and of course, it depends on the country. But what I think you're trying to say here, which is extremely important, is that we do have the tool to select the best pump by using that website. And inside of the website, if you are providing the correct information about your project, and we are talking here about the electrical engineers, if they are going inside the website and selecting the location and mentioning how many cubic of meters of water per hour we need, and how many hours do we believe the sun will shine, 6 hours, 7 hours, 5 hours a day. And also, Ben, what you mentioned, which is very important, is we want to know the worst case scenario. So January happened to be in some of the countries the worst months, because that's when we get less radiation, when we get more rain. It's not the same for all countries. So maybe in your country, it's May or March, but you do want the website, this tool, to calculate for you the worst case scenario, because everything else will just be better.
Correct. Okay, we're ready to move to the next page. So just like Shai mentioned in her presentation, we can calculate using an equation what is this pipe friction loss. It's also a tool you can use it here. You can see that by putting, just a second, by putting the material, the diameter and the length, it automatically calculates what is the loss we have when moving the water towards the tower. Okay. And now you can see, I can insert what solar panels I use in the data sheet and save it in the website. Just this is why we need to sign in. And this is the way we can use the website again and again if I'm using the same solar panels, and the website will remember me. I can show you more in the next slides. So how do we choose solar panels? This is an important part of the electrical engineer, and we need to be concentrated and realize how it is important. So the first thing we do is we looked at the Bloomberg Tier 1 list, and we see the brands, and we check what brand we can get in our local country, in our local supplier. The solar panels we look for is 270 watts to 330 watts. This is the power of the solar panels. You can see the connections we have. We have two kinds of connections in a water tower, in a water project. The first one is series. I'm not going to get inside all the electrical technology and stuff, but this is the first one. You can see it's all connected. You just multiply the power by 8 if it's 8 solar panels and multiply the voltage, and the current remains the same. The first one, just to make sure, 270 watts is the power, 8.52 ampere is the current, and 338.8 volts is the voltage. Now here you can see another connection we have in a water tower. It's, I'm going to elaborate in the engineer presentation, which is a connection of series and parallel. You can see 6 panels connecting in series, and they're connecting parallel to another 6 panels in series. I'm not going to confuse you. Here you can see the list of Bloomberg TIG1 solar panels. This is the approved solar panels brands to use. This is the best panels in the market. And if you choose one of the solar panels from here, we can be calm and realize we have the good solar panels, and we can be assured that it's going to be a good solar radiation with the solar panel, just like they mentioned. I chose Jinko just for an example to show you how to observe the data sheet. Don't panic if you see all the numbers. I'm going to walk you through. So here you can see I chose the middle column. It's the 270 watts. Now, watts, just like I said, it's power. Here you can see 2 columns, STC and NOCT. STC is standard test conditions. As you may know, if I'm sitting in my lab and I'm planning solar panels and I'm going to Cameroon, the same condition I'm putting in my lab and in the field in Cameroon won't be the same conditions. And this is why they mention the standard test conditions they do in the lab, which is radiation of 1000 watts per cubic meter, which is very high. And the cell temperature is 25 Celsius, which is very low, because if the cell temperature is 25 Celsius and the radiation is strong, it's almost impossible. Because if the radiation is strong, the temperature is also strong, higher. And the higher the temperature is, the efficiency decreases, okay? So it's very important to remember that. So what else they give us, the solar panels companies? They give us a normal operating cell temperature. They give us another example of a normal temperature. So as you can see, the radiation is less, it's 800, and the ambient temperature, the temperature outside is 20 Celsius. If the temperature outside is 20 Celsius and the radiation is strong, the cell temperature will be higher. It will be like 40 Celsius. So the efficiency will decrease. And you can see it in the columns. If I'm looking at 270 watts STC, you can see the NOCT, the normal operating, it's 202 watts. And also the voltage decreases and also the current decreases. So what we do in our project is we looked at the most strict position. We need to be careful that we don't pass the pump voltage, the voltage warning they do, and I'm going to walk you through it. So we look at the higher temperature, the higher voltage, which is 38.8 OC. Also, I'm not expecting people that don't deal with electrical engineering to understand everything, but you just need to be aware that there are 3 parameters, which is voltage, current, and power we need to be aware of, and we don't want to exceed the warning of the pump manufacturer. Sorry.
Basically, what you're saying is that we don't want to install too many solar panels because that's going to hurt the pump. So we have to be careful about the number of solar panels we're installing, but at the same time, we don't want to install so little because then the pump is not fully operating. So this is important, and this is why the job of the electrical engineer is crucial, because we want to make sure that we're choosing the right solar panels and the right amount of solar panels. And this is the key.
You're right.
And
we
also,
need to find the sweet spot, which is as much power as we can without damaging the pump. Yes, Meir?
Yeah, I was just about to add the right amount of solar panels and also the right connection to connect them series and parallel the right way. This is what Ben showed in the previous slide. It's also very important.
Now you can see I looked on the data of the solar panels and I inserted to Grundfos website. The following you see, it's the Jinko solar panels we just looked at, and now I save it. So Grundfos will have my data. I don't need to do it again in the next project. Now we're ready to start sizing. And Grundfos offers me the following pumps. As you can see, it offered me the first pump we talked about. It's SQ Flex 3A10. And it also suggests the number of modules, the number of solar panels, and it gives me more data. When I choose the product, I will get inside the curve of the pump. Here I can see, this is an example I put of Austin Rashid from Malawi that sent us. Also, all the Malawi team doing it great, also Robert and Moses. As you can see, we have the IA template and symbol. We can see who made it. You can see Austin Rashid name, so I will know who to address. And you can see the working point, nominal point that you already filled in, which is showing me also the flow rate, also the power I need to power with the solar panels, and the TDH. On the left side, you see the pump, just like we mentioned. And on the right side, I can see the specification of the pump, which is very important for the engineer, the electrical engineer, to look at. So we will know what is the current, what is the voltage, and what is the power I need for the pump to work in the best way without damaging it. Now, what I put here, on the left side, you can see the data, the specification of the pump. And on the right side, you can see the specification. On the right side, you can see the specification of the solar panel. And this is how we fit the solar panel to the pump. You can see in a circle the nominal power input, which is 1.4 kilowatts. You can see the voltage, which won't exceed the limit of 300 volts. And you can see the nominal rated current, which is 8.4 amperes. Now, I look at the solar panel I suspect of choosing, the 270 watts Jinko. And now I look, if I choose 7 solar panels, I will get to 1,890 watts, which is higher than 1,400. And it's good because we want to choose solar panels that will work also in the morning when the sun radiation is less. And also if it's cloudy, we will be ready for the worst conditions, just like we mentioned. So we need it more. How much more? In our opinion, it's how much more we can without exceeding the voltage limit, okay? In general, in the electricity solar panel world, it says that you need to choose at least 30% more than the nominal output power. But we choose, just like I said, using the voltage limit and the current and the power, and this is how we know how to choose. Also, you can see the current is 8.52, which is higher than the 8.4, and it's a good also. We want it to be good. Why? I don't know why it's okay, but won't exceed the fuses. Why? Let's say I'm using a pump and I have the controller. We also need to be aware of the controller limit of current. And I'm going to touch it in the next slide, because the controller maybe have a limit of 10 amperes, which is true for the CU200, let's say. And it has a fuse inside, which will burn the moment it will exceed the 10 amperes. So the electrical engineer need to be aware also of the controller limits, so we won't burn out the controller. Now, this is the controllers we use. This is the SQ Flex controllers, the DC pump controller we use of Grundfos. So the first pump we talked about, the SQ Flex 3A10, uses a CU200. You can see the limit is 1,400 watts. If we have a pump with a nominal power of higher than 1,400 watts, we can't use this controller. We'll have to use the next controller, which is the SQ Flex CIU 903 on the right. Okay, now the thing it will give us, the controller, the first thing is system monitoring. We will know how much power the pump consumes. I need just to remind you, the controller sits inside the pump room. So we can enter the pump room and we can see directly how much power the pump consumes. The next thing we can see is the alarm indication. If the pump is in higher voltage or a higher temperature, at the moment we will see it on the controller. And the third thing, which is very important for us, is the level switch. The floating switch and the pressure switch, we connect it directly to the pump controller. This is how we control the pump and shut it off when the tank is full. We will elaborate in the future. And I wrote you on the bottom that the CU200 fits the SQ Flex 3A10, and the controller on the right fits the other 2 SQ Flex pumps, which are higher. Now, we know that we have projects that we have to use an AC pump, just like we mentioned. So when we use an AC pump, we need an inverter because we need to invert DC electricity to the AC electricity. So the two mostly common inverters we use are the Grundfos inverter, just like the pump company, and the Daylif inverter, which is an African company, which gives us the same abilities. Now, if you remember a couple of slides before, we choose the solar panels according to the pump. And what is different in the AC is first, we need to choose the inverter that will match the pump, which is very easy because we looked at the nominal power of the pump. Like, let's say the SP525, we can see in the specification, it's right, 2.2 kilowatts. Now we know we need to choose an inverter, which the name is very simple, it's 2.2. RSI 2.2, Daylif 2.2, very simple. The 5A33, if you look at the specification, it will write P2, the power is 3 kilowatts. So we need an RSI 3 kilowatts, okay? And the next thing we need to do is fit the solar panels to the inverter because we have another thing on the way. So this is different. Just like we power in the DC directly the solar panels, the pump, here we need to power the inverter first. So we need to look at the inverter specification and choose the solar panels according to it. Now we get to a more interesting part, our pump room, just like Tal mentioned in his lecture. Now we have the electricity components in the pump room. So just like I mentioned, the first one is the controller, which gives us the ability to control the pump and the system monitoring. It connects the floating switch and the electricity to the pump runs through it. And the second thing is the Israeli remote monitoring box. We will elaborate, and the electrical box. As you can see, all of the components has an earthing cable that connects to the 8th earthing rod. If you remember Moti's lecture, so we need to connect everything to the earthing rod, and this way we can keep the potential as we want. Okay, now the control switches. Just like Tal mentioned, we have the pressure switch, we have the floating switch, and the mechanical valve. Now you can see in a very simple way when we use each of the components. The floating switch shuts down the pump, the pressure switch shuts down the pump, also in 2-tower project, the floating switch in a 1-tower project, and the mechanical valve we use only to close the pipe in a 2-tower project. Now you can see everything. So as I told you, 1-tower control. The water floats towards the tower, and when the tower tank is full, we have a floating switch located inside the tank that shuts down the pump. The moment it will get to the higher point, it sends an electrical pulse to the pump controller and then to the pump, and it shuts down the pump. And then after they use the water, the floating switch goes down towards the bottom, and then it automatically turns on the pump when it says we need more water. Now the 2-towers control is more complicated. We have 2 components, a mechanical valve and a pressure switch. We put a mechanical valve in each of the tanks. If it's a multiply tower, each tank must have a mechanical valve inside. The mechanical valve, the moment, it's a very simple, I will elaborate in the presentation of the water control, but just for a basic knowledge, the moment it gets to the upper level and the water is full, so the tank automatically in a mechanical way close the pipe. And the moment we have the first one, okay, this is the most basic diagram. So the first thing, we have water flowing towards both of the towers. And obviously the first tower tank gonna be full first. So the mechanical valve closes the first tower inlet. So now all the water is going towards the second tower because the first tower pipe is closed. And now all the water is going towards the second tower. And the moment it's full, also the mechanical valve in the second tower closes the second tower inlet. And now I have 2 tower tanks. Both of the pipes are closed. The pressure rises because the water doesn't have a place to go. So the pressure rises. So I have a pressure switch which shuts down the pump because the pressure rises and exceeded our limit. How do we know how to limit the pressure switch? We need to calibrate it. We have another lecture on it. The water engineer can calculate before the project in the design process and tell you, listen, when the pressure switch gets to 70 PSI, you can calibrate the pressure switch to shut down the pump. And then when the pressure goes down, let's say 30 PSI, it will turn it back on. We have another occasion, which sometimes we will use the timer. because we don't use the pressure going down. Let's say after half an hour, we need to decide on each project specifically. So after the pressure switch shuts down the pump, a half an hour passes, and now it knows to turn back the pump. Everything is clear? Okay. Now, after we finished all of the design process, now we have the final BOQ tab to approve.
So hold on, just to repeat, Ben, everything we saw until now was just what the electrical engineer has to do when it comes to the design, meaning he has to make sure that the pump that the contractor is suggesting and that the water engineers are suggesting is the correct pump. He has to decide how many solar panels we need to buy and what kind, and he needs to decide how many floating switches, mechanical valve, what else do we need in order to make sure that the design is well done, correct? We are only at the first step.
Yes, correct, definitely correct. And now, after we saw everything in the design, all the electrical components are correctly as we think, and after design, we have the BOQ. Now, the BOQ of a water project has to go through all the departments of IA. The hydrology department, the water department, the construction department, and the last department that we need to approve is the electrical department. We are the last place to approve. So you can see the template of the solar template, BOQ. Just a second. Oh, it's not working. Just a second.
So it is inside of all of the BOQs, the master BOQs, all the BOQs that are already inside the files. You're going to see one page called BOQ number 7, which here you have all the different equipment and items that the electrical engineer has to make sure that they are correct.
Correct. You can see the submersible pump. You can see panels in quantity. So we need to fill what panels we use. What type, you need to make sure the floating switch, if there is, the pressure switch, valves, mounting structure. It's important to note that I saw a lot of BOQs that the contractor sends us the pump and the panels and the mounting structure together in the same line. And it's not a good thing. We want all the contractor to send it in a separate rows, so we'll know how to calculate if it's true and if the cost is right, okay? Okay, so just like Sivan mentioned, now we're in installation part. After we approved the BOQ, we started installation, and now the electrical engineer goes to the site for the first time after the pump room construction is completed, and you need to ensure all the electrical components are according to plans. We have the grounding system, the water meter, control system, like the switches, the monitoring box, the lighting, the lights, and everything. So the first thing we need to do is measure the grounding system. We need to check that all electrical components in the pump room, including the lighting arrestor, electrical box, monitoring unit, pump controller, are connected to the foundation and the grounding system. You can see on the right, this is the grounding system. You need everything to be connected to it. You need to measure it also. Now, the second thing is the water flow meter verification. We use in Innovation Africa 2 water meters, Israeli water meters we supply to you. The first one is the Arad Multijet magnetic meter, mechanical meter completely. And the second one is the ultrasonic meter, which doesn't have a mechanical moving parts. We need to, just to make sure, we will use both of the water meters. The fact that you got the ultrasonic meter doesn't mean that we don't use the magnetic meter, because it's really good meter, and you will get it also in the following deliveries. Here you can see we arranged also a presentation about each of the meters. You can put a link to it, enter it, and you can see the data. You can see the nominal size, including the plumber. This is 30 millimeters. This is the ultrasonic meter, it's the same. Just to make sure we need the adapter. You need to make sure the plumber, just like in the pump room and everything that Tal mentioned, just on the right size, or we need an adapter. And you need to make sure also that the flow is in the right connection. You can see there is an arrow inside each of the water meter, and we don't want it to be upside down. Yes, Sivan?
And also, Ben, I want everyone to pay attention to the link on top of your presentation here, that slide. Do you see that link? Meaning that we have another presentation for you, but not for today, only about water meter. So you're going to see that inside that presentation that we're going to send you later on today, you can also click to go inside an even more in-depth presentations. So everything is here. And again, in the next few days, we're going to go in more depth. Thank you, Ben.
That's true. Here you can see also from the diagram Tal showed you the location of the flow meter. This is in a single tower pump room. You can see it here. Here you can see a demonstration from South Africa of the location and a picture of the pump, of the water meter, sorry. And here you can see in South Africa, they use UPVC, but in other countries we use steel, so don't be confused. And the next step is, like we mentioned, the switches and the mechanical valves. So we need to make sure if it's a one tower, we want all the electrical engineers to see also the floating switch located in the tank, and also to check that it's connected to the controller. We need to make sure that you see the connection and it's working also test it. And in the two towers, we need to make sure that every tank has a mechanical valve installed in the tank, and a pressure switch is installed in the pump room as the following. Also, we need the way you calibrate the pressure switch is by using a pressure gauge. We also have it already in the pump room, so you can use it to calibrate. Here you can see in a one tower control, just like I mentioned, the floating switch is inside the tank, and it's connected to the pump controller, which is inside the pump room. In the two towers, we have a mechanical valve in each tower tank and a pressure switch inside the pump room, which is connected to the controller. And here you can see a diagram of the pump room in a multiple tower pump room. And you can see that the pressure switch is on the second tower pipe. The reason we put it is that we want the pressure switch only to shut down when the second tower is full. So that's why we put it on this pipe. And this is the way it signals it the best way. Now we got to the Israeli monitoring system unit. You can see it's also located in the pump room. It's another electrical component. Just to mention, this is the way we use it right now. In the future, we're going to change it to another way, which I'm going to show you in a couple of slides. It's located here. You can see it's also connected to the earthing system. Right now, it needs a 40-watt auxiliary panel just to power the monitoring system. Just to make sure, we had a couple of incidents where they put it wrong, the 40-watt auxiliary panel. They put it like a picture on the wall. So we want it to be in the same height of the solar panels and the same tilt and direction of the solar panels we already put for the powering the pump. It powers only the monitoring box, the IA monitoring box. In the future, we're gonna lose it and use a more a nicer technology that we won't need to put the 40-watt auxiliary panel, and we will only use the panels powering the pump. So this is the components of IA's monitoring system right now. You can see we have a cellular modem, because the way it works, the monitoring system, there are two components that sense the technology, that sense the situation, which is the electrical meter that sends the power coming from the solar panels. And the second one is the water meter that is also connected to the monitoring system. And this is the way we can get monitoring for a database of both the electrical aspects and the water aspects and the flow meter. So we use a cellular modem in a SIM card inside that sends it to our website so we can monitor everything. We have a charge controller and a battery just to power the monitoring units at all time. And we have a converter just to use the power efficiently. This is the way we connect it. As you can see, we need to connect the solar panels directly to the DC meter because we need to sense and monitor the solar panels array. And we also can sense the pump, the solar pump consumption. This is why we also connect the solar panel power to the water, to the electrical meter. And you can see in the green arrow, the water meter that is connected to sense the water flow rate. And the power of the system, we need 40 watt aux solar panels on the right. Now, just like I told you, this is going to be the future monitoring system. As you can see, now the box number 1 also will be in the logo of IA. Why is that? We're going to give both the monitoring box and the electrical box directly from our lab, and we're going to install and assemble everything and send it to you in a one box containing the two of the box, also the power box and the monitoring box. And you can see we don't need a 40 watt auxiliary solar panel anymore. Why is that? We have, you can see number 3, we have a converter power supply that is gonna switch, they're gonna replace the 40 watt auxiliary panel. How does it work? We get the solar panels we already have to power the pump, and the converter will just convert the power from the solar panels to a smaller power bank to use only for the monitoring system, because we don't need the power, so high power to power the pump. We need a small amount of power, so it converts it. Now, the first box is the high voltage. You also separate it for a security reason and just to be cautious. So the first box is high voltage and the second box is low voltage. This is the low voltage, just to make sure. Also, another thing we're going to supply from you in the second thing is that we have the security lights, the service lights inside the pump room. We're going to supply to you from Israel. Using the high technology lights, we're going to give you in the same box with the two box. It's going to be inside, and this is how you connect it to the high voltage box. And you don't need extra components. You just put and insert the security light, the service lights inside the pump. I'm going to show you in a couple of slides more and elaborate. You can see the low voltage also with the modem, charge controller, and battery. So this is the service light I mentioned. Just like I said, currently we buy it locally, but in the future monitoring system, we're going to supply it for you, the service lights, and inside the box, you're going to be the battery and the 40 watt power supply inside. Now, there's going to be a light outside the pump room and inside the pump room.
So Ben, just to make sure that everyone understands.
Yeah.
So right now we just finished with those 3 components that we are installing inside the pump room, and now we're going to be talking about the light. Why do we need light inside the pump room, and why do we need light outside of the pump room? And oftentimes I heard that the guards, we're paying a guard to keep the solar panels, but the guard doesn't want to stand there in the dark. We have to make sure that we're installing light bulbs inside and outside of the pump room, but even more, and Ben is going to show us, we also need to install what we call security light. So what we're going to do is the following. Right now, please continue to do what you do. Buy locally those light bulbs, the batteries, and everything. But in the future, we are going to be sending you excellent light bulbs from Israel, and everything will be integrated inside of those a few boxes that we are already installing inside the pump room. Ben is going to explain what we currently do and what we're going to be doing in the future, but this is important. You must install lights inside the pump room, outside of the pump room, and the security light. Ben, continue. Thank you.
Yes, just like Sivan mentioned, it's very important that currently you buy it locally. It's very important to insert the service lights inside the pump room and outside. But in the future, we're going to supply it for you, and you just need to connect it in a correct way. And most important also is the security lights. Now, what we did here, you can see there's a light, a very strong light outside, a security light. It's going to act like an alarm. Once a person approaches the tower, the light will power, a strong power that also people will see that someone approaches the tower. Now, what we want, there's a requirements we put in, and some of the countries already have a nice security lights they found from the contractors. But we encourage everyone to find a security lights with the following requirements, which is a LED light bulb, solar panels connected inside the light, so we don't need an extra component. The battery charger also part of the light fixture, it's inside the lighting, and a motion detector sensor. So once someone approaches the tower, it will automatically turn on. And also we want it to turn off automatically during daytime. So we need an illuminate sensor. This is an example of what I just mentioned. As you can see the solar panels inside the lights. And if any one of you don't have lights like this in their country, please contact us and we will find one together with you, because it's very important for us. We can supply it to you from Israel, and it's best for you to buy it locally, but find it with the requirements I just mentioned. Okay, the final step of the electrical engineer is the final verification and approval. The electrical engineer must test all of the components I mentioned. First is solar panels array, the grounding system, the security lights, the pump and pump controller, and the remote monitoring system. Now, how we do it? We take a multimeter, which can measure everything in an electrical way. We measure the solar array output, the voltage and current. And it's very important, the measurement should be done when the solar radiation is strong. Please do it in a sunny day, in the noon, not in the morning, not when it's cloudy, because this is the way we can make sure it's according to the power specification and what we meant when we designed the system. Also, you need to be aware of the series and parallel connection, so we'll know what we really meant the power to be, and the voltage and the current the same. Now, the grounding system, you need to measure the resistivity of the earthing bus. Just the earthing bus connects all of the electrical components, so we need to measure the earthing connection of all the components using a multimeter as well, and see it's according to plans. And the security lights and service lights, we need to check that all the security lights are working, and you need to check the sensor is working. Also approach, also when it's light, that when there's a light, it turns off, and check everything is working. And the pump and pump controller. Just like I told you before, the pump controller can tell us if there's any fault, if there's any error in the pump. So you can see the F1 is over voltage, F2 is over temperature, no contact. So we need to see the pump controller, look at it and see it's sending you a pump consumption of the power and not sending any error. And if it's sending an error, you need to think what we need to do in order to fix the pump because it's not working appropriately. Now, the remote monitoring system, it has two aspects. The first one is the voltage. We need to check the electrical supply we give it. And the second thing is the cellular modem, that it's working. You can see the lights are according to plans and the voltage is also correct. And most important is to check the monitoring unit is sending good readings to the server. We need to check via the phone application we have and check the water pump is working. So we need to get both energy, good readings, and water reading. After we get both of the systems, we can be sure that the monitoring system is working according to plans. If not, contact us so we'll know what we need to do in order to fix it. It's very important for us to see the monitoring system. It's one of the most important things in a water project, both for us and both for our donors, so we'll know what is the situation of the project. Thank you very much.
Ben, I gave you 2 hours for that presentation, but you finished it in 1 hour.
Yeah,
just terrific. Wonderful, wonderful. Thank you, Ben. Excellent, excellent job. I think you gave us a very clear overview about what the electrical engineer has to do when it comes to a water project. Thank you very much. So we have a choice. Either we take the lunch now, and then we come back and answer a question. Or if you don't mind, we can take another 15 minutes because we are early actually, and we can answer some of the questions. And please keep in mind, once again, that we're going to go in much more in depth in the next few days. So maybe Tara, let's take a few questions now, if you can help us.
No problem. I don't think we have that many questions this time, so I think if we can just take 10 minutes, we'll be good. Okay, let's start. By the way, excellent job, Ben. Wow.
Thank
I'm
you.
impressed. Way to go. Sivan, you've got some new presenters in under your course. This is awesome. Okay, so Dale from Uganda asked, DC pumps without the CU200 is impossible to connect to the floating switch. Any response here?
I didn't understand the question.
He said the DC pumps that you were talking about in the beginning,
Yeah.
without the CU200 is impossible to connect to the floating switch.
Okay. So please install a CU200 to the control pump.
Correct. Actually, Tara, that question,
Yeah.
sorry, that question was sent before Ben
Before
showed
you went
us.
through all the SQs. Okay, fantastic. Also, the Tanzania and Uganda team mentioned that the SQ Flex pumps are not common and available, but thankfully we saw the Malawi team hop in and they're going to be sharing their suppliers. So I hope that we can find across all our countries suppliers for these
Yes,
SQ pumps.
it's very important comment. Please, I encourage all of the countries already now to contact the suppliers and contractors so we can get the pumps we want now, because it's possible to get it in Africa. So I'm sure they can get it, but we need to already tell them we want the pump so we can get it in order for us to get the project. So please contact the countries right now.
And why is it important? It is important because if we are going to continue to install the same type of pumps we have installed until now, it's not good enough because we're not taking advantage of the yield from the pump, from the borehole. If the borehole gives us a yield of 1 liter per second, so let's use a pump that at least can pump that much of water. If you're installing a pump that can pump less, it's sad because we're not providing the people with the amount of water that the borehole can provide. So always try to match the pump to the yield of the borehole. If the borehole can give us 5 liters per second, then get a bigger pump. And this is what we're trying to do. And I'm sure that Guy is going to help us because Guy will gonna try to help us to be more organized. Maybe not this year, but in the future, we would like to order containers with many of the pumps that we need, many of the solar panels that we need. Guy will help us to organize the supply chain of all of those type of items that we are constantly using in many of our projects. So if Guy will agree, we're going to try to do it as soon as possible.
Another thing to mention, also there's a cost-wise that some of the project already done. We choose an AC pump that we could have choose a DC pump that will give us the same results, the same flow rate, but we can cost sometimes $5,000 or more. We can use the money for other projects and get more people water. So it's a very also in a cost-wise, we can use less inverter, which costs a lot of money, less solar panels, which is also less money and complicated. So it's very important also the thing we need to mention in a DC and AC selection.
Love that we have to do like project cost analysis for every single project. Speaking of Guy and organizing us, he had a question about whether or not we track and measure the pump fault rate.
Actually, we have Sagit and also all of our electrical department. We monitor all the projects. We have monitoring system. So every time a project fails, we have Sagit to tell us it fails and contact our local engineers so we can go and fix the pump. And another thing we do is monitoring the system according to realize future installations so we can see how we can improve in our design. I hope I answered your question.
The way it works now, and Ben, tell me if I'm correct. If the pump stops working in more than 36 hours or 48 hours, I'm not sure, I think in 36 hours, we get an alert. Is that correct?
Yes, it's correct.
Correct.
Definitely.
And then we have Sagit. Sagit, please say hello to everyone and mute yourself.
Hi, everyone. Nice to meet you all.
And Sagit, she is the police, because what she does, she analyzes those alerts, and she's trying to figure out what went wrong. And then she calls our electrical engineers and she tells them, go and check the water meter, the monitoring system, and that's what she do. So her job is to make sure that all of our alerts are being fixed.
I will also add that, Guy, we can work together if there's different levels of monitoring, more levels of monitoring beyond what we currently do that we can add and pull the analytics from when we're doing the monitoring of our projects. So I think that there's definitely room for us to specifically improve on those certain areas, for instance, like pump fault rate. So yeah. Moving on. So Daniel asked, if I got you right, while designing and choosing the number of solar panels, and the calculations are made considering the most unfavorable solar conditions, like cloudy months with little solar energy, my concern is this: don't we risk the power of the solar panels if they're going to destroy the pump when it'll operate in favorable conditions?
You're right. You're completely right. Another thing to note is that once we get the data for Grundfos, we don't go blindly and just to choose the solar panels. We need to also do all the calculations by ourselves. So we don't rely on Grundfos. We just take the recommendation they give us. But after that, we're going to go on the data, just like I showed you, and select it by ourselves, the quantity and all the specification. So that's a right question.
Okay. Another one, Indifili in South Africa asked, is it a must to weld the grounding rod to the foundation, or can we tie it with the wires like how we tie the rebar? Is it a must that to weld the grounding rod to the foundation? Yeah, same thing. Yeah. Did that make sense, Ben?
Meir, do you want to answer it?
Yes, it's in the construction manual. It should be done according to the construction manual. You should be there should be a ring welded on the construction, and the rod that going down to connect to the ring to the bus bar should go all the way and be welded to it as well. The dimensions and the material are all on the construction manual, and we should follow the guidelines there.
Okay, Menzi asked, how much power do the accessories require so we can know the number of additional panels we will need after sizing the pump?
So you don't need to consider it at all. It's not an issue. Just think of the pump.
Okay. Then the South Africa team asked, in South Africa, we usually install a few other extra electrical components such as electrical fence, security alarms, etc., that need power. Many times the contractor would use the same solar panels that power the pump to power additional components. This is done to avoid adding an extra solar panel, usually a smaller one. Your comment on this, please.
Yes, so actually South Africa components are something different from all the other projects we have. So we need to look at all of the components and electricity specification to see what we can do regarding the other components you mentioned. But it's a correct question, but it's also need to be considered specifically for South Africa projects. Okay. We need to do a meeting and understand what are the components and how we can power it.
Yes, so just for those who are wondering why South Africa is different, just because we have more theft, unfortunately. So we need to install electrical grid, we need to install strong alarms, and because of that, we need more power. It's a bit more complicated, and this is why for those electrical engineers of South Africa, the job is a bit more complicated, but necessary.
We should definitely take this into consideration when we're reviewing the BOQ, the electrical sections, that those particular items, if we know at that stage, to include them so they can be a part of the analysis. Okay, so Eric asks, are we strictly going to stick to the 270 watt and 330 watt solar panels? Only because in cases where a system is big and may require many panels, then selecting bigger panels would be ideal. That's in minimizing space usage, etc.
So it's a correct question. I also discussed Meir with him before the presentation, but bigger panels also have higher current and higher voltage. So it's possible to use them, but we need to consider if we don't pass the specification of the pump, because we may use a higher 400 watts solar panels, but the current will be too high for the controller, so we will miss our point. But we need to consider it. Also, we need to check if we decide, let's say we have in Malawi, I don't know, Jinko solar panels. So I can see there's 270, 330, and 350. I need to check how I maximize in the most efficient way the quantity of the solar panels so I can get the maximum power without damaging the pump. So we can also rely on different power of solar panels.
Okay, this is a really good question from Rachel in Uganda. What's the way forward to old projects that don't have electrical protection, like controllers and circuit breakers, and can these be provided?
That's a nice question. Also, we have a couple of projects. We were in Zambia in July when we visit. So yeah, we decided let's put the CO200 because we were there and we can install it, a controller, a circuit breaker. But it's a good question. We need to think about it. And also,
can I interrupt? Circuit breakers and fuses are a must. If they were not installed in older projects, we need to go back and install them. By the way, it's very simple, cheap, easy installation to do. Electricians should not work on the controller when there is no circuit breaker to disconnect the panels from the controller. It's not safe. So circuit breakers and fuses must be done in all countries. We will need to make a list of the project who still doesn't have them and go and do that.
Wando asks, what's the maximum distance that we need to consider between a borehole and a tower when selecting a pump? In this case, AC pump.
What is the distance? I didn't understand the question, sorry.
What is the maximum distance that we need to consider between a borehole and a tower when selecting a pump, an AC pump?
I think he's talking when we have to connect the borehole, the solar panels to the borehole when the borehole is far away. How far it can be?
Mm-hmm. It's a good question, but I don't think it's a matter of electricity so much. What do you think, Meir?
I agree. We can calculate the voltage losses even if you go DC or AC. We can take that under consideration. We will also need to put the economical circumstances. How much money does it cost to put armored cable in the ground and decide. It's not a big issue.
The short answer, because I looked into it, it can be 200 meters, can be 2 kilometers. It doesn't matter, meaning the electricity will go through. The question is money, because the more we're installing the armed cable, the more expensive it is. So sometimes it might be easier to just install 2 towers instead of doing just 1 tower and a very long cable to reach the borehole. That's all. It's more about money and less about the electricity usage.
Okay, I think we just have a few more and then we'll wrap up. Karabo asks a recommendation on the grounding system, Ben. For example, in South Africa, we usually use the SQ Flex AC pumps control by VSD, which consists of components like choker, which in most cases causes interference with the monitoring unit and causing failure to send data if not grounded.
Actually, in South Africa, the big question is why we use VSD, and we need to consider stop using VSDs. It's also a thing we need to note in the following year, and we will discuss it further in depth together to realize maybe we should stop using it. Yes.
On the same note, I think, question from Meir. I don't know if you answered this already. The last time I installed a monitoring unit in one of the projects in South Africa. Okay, I think this was we struggled with getting signal. We then switched to the local SIM card. My question is that about data going to be loaded from your side in Israel, or should it be done locally?
You want me to answer, Ben?
Yeah, it's for you.
Yeah, okay. So we started this year using also local SIM cards in some of the countries due to many reasons, communication issues and other. And we decided that in each country, when you use local SIM card, you charge it locally. If possible, we will help you with the cellular provider, or it's the country manager role to contact the cellular provider and to get good deals from him, meaning deals that will enable us to automatically renew the SIM card every month so they don't have to call or to upload enough bundle of data that will last longer. It's on the locals, but we need to make it more efficient so we will not have this situation that at the beginning of every month or after a period, people in Africa need to sit and to upload bundles of data. It's a headache. We don't want to cause you this headache. So we'll have to make it more efficient, but it's on the local team.
Sivan, we have 3 more questions. Do we have time?
Absolutely, absolutely. On the schedule, we have until 1:15. We have another about 25 minutes, but yes, let's answer another 3 questions and then maybe we go for lunch a bit earlier.
Fantastic. Okay, so Keith Malawi asked, what happens if the system only requires 5 panels? Aesthetically, we were told it does not look good and it makes the tower look incomplete.
Question for Sivan.
Sivan.
I couldn't hear the beginning, sorry, Tara.
It says, what happens if the system only requires 5 panels? We were told aesthetically it's not pleasing.
I will add, we put 6 and we disconnect this, we don't connect the 6th one. We put 6 panels, so aesthetically it looks good, and we connect only 5, not to size.
Good solution, Meir. Thank you.
Yeah, did you talk about like the energy required to power the monitoring unit and what we want to do with the panels, etc.?
There is the current situation where we power it with auxiliary 40-watt solar panel, and there is the future situation starting this year that we are going to steal 60 watts from the main array, but it shouldn't affect the solar array or the pump operation. It's 60 watts that, again, we need to charge at the end of the day 95 watt-hour battery. It's nothing. 95 watt-hour battery. It's nothing.
So Tara, yeah, just to make it clear, until now, we had to install a small solar panel just for the remote monitoring system, but we don't have, we're not going to do it anymore. We're going to use those solar panels that we're already installing to monitor, to provide the energy to the monitoring system. And Meir this afternoon is going to show us live all of those components inside of the monitoring system. Is that right, Meir? We cannot hear you.
So Jeremy solved the camera issue. We can use that. So we are halfway there. We will use the lunch break to do it. Yeah. But let me say one thing, and I'm happy that all of Innovation Africa team is here on this call, because regarding the monitoring, the water monitoring, we want to do a lot of projects, and we want the water monitoring to be as efficient as possible and to cause less headache as possible. Now, 2 things were problematic, the way we currently do things. The small solar panel was a headache. It's very hard to mount it on top. Also for our electrician and for the contractor, that's one headache. And the second, the water flow meter, since the contractor didn't have it on time, we need to go afterwards and break and put it inside, and we couldn't go on with these 2 things. So the 2 solutions for them is no more small solar panel. And the second is we will send a lot of water meters in advance for the contractor to install at the right moment and for you to supervise that he actually installed it.
So when we're talking about calculations for solar energy, we also need to give it another 60 watts, right? In the panels.
No.
No, we don't need to consider it. It's not.
No, okay. It's not relevant enough. Okay. All right. 2 more questions. Okay, so Eric in Uganda is asking about instances of component thefts on water projects. i.e. pump controllers, pump houses, is it possible to install alarm systems on some of these prone projects? South Africa's been our guinea pig in the alarm system. Sivan, Meir, do you want to speak to that, to the efficiency of those alarm systems?
Maybe Ebram can tell us about this alarm system. Ebram, are you with us?
Afternoon, Sivan. Yes, I'm here.
Please tell us about your experience with alarm systems in South Africa. I know you have some interesting stories to tell.
Yes, good afternoon, everyone. In terms of the alarm systems, I would say from the beginning, it was a trial and error. One of the reasons is because, as Sivan indicated, we have a theft problem in South Africa. So in the beginning, we started with our first alarm system that we installed. It was, I think it was Paragon, if I'm not mistaken, Paradox. It was not the best alarm that we could find in the market. It had its own fault. For example, it had a smaller siren. It was a 15 watt. It couldn't sound enough sound for the entire village to be able to respond, because remember, our sustainability model relies on the community. So with that smaller horn, it meant that they couldn't get the sound. The second thing that we found, which was a bit of a challenge at that time, was that it was relying on the radio that they installed, needed the community to load, I think, SMSs into the system. So the failure of the community, remember they are poor, so their failure of loading those SMSs meant that the system couldn't notify them. So even if the guys that come to steal would break in, so they would break in and they could not get the notification. So we had to move away from that. Now we are using the IDS alarm. Of course, also it had a challenge because the first installers, now it was a human error in terms of installing the IDS system. They did not install all the components that we needed to be able to make that system to be much more effective. So we had to move from one contractor, because of the trial and error, we had to move from one contractor to the next. Now we are using an alarm that comes from Techno. We moved from ADT, which at that time, we thought ADT, because it's an international organization, they are also in Israel, so we thought it's going to assist us. However, the version within South Africa was not as effective in terms of installing, because they installed to us an alarm that was not effective in alerting the village still. The other part, which was a bit of a challenge in our context as Innovation Africa, was that they wanted us to pay a monthly fee, which we couldn't afford as an organization. We can't in any way commit to such, because it means every month we have to pay that company. So we're looking for a better package that we can install once off, and the community can simply be able to just maintain it as it continues. Now we are using a company called Techno. Still, we are still under trial and error. Things that we have improved are the following. One, we have installed a bigger siren, a 30 watt horn. It is able to sound to the entire village. They are able to come. And secondly, now the second thing that we've improved is that we have installed an app that is you are able to arm and disarm the alarm on your phone. So that is the second. We are monitoring it to see how effective it's going to be. So that is where we are up to this far. We have installed also electrical fence, which is not part of the question, because many people are stealing in South Africa, specifically in the Limpopo region. But in the other regions, there's no theft, so things are going very well. That's how far we have gone. Unless if I've left something, Adela and the entire team can add anything that I've left out.
We also gave guns to the guards, but even that doesn't help. I mean, not real guns.
Not guns, the pepper spray guns.
Pepper spray guns, yes. So
but we also, we added a panic button for the guards. I don't know if Abraham mentioned that. so that, because and many times the people that come to steal things do actually have real guns. So for the guard to, if they feel that they need support from the community, they also have a panic button that also starts off the sirens, and so it calls the community to come and help him out. But it's all been test and fail and test and trial, and we're working on it.
Thank you, both Adela and Abraham. Thank you. Tara, maybe one more question and then we go for lunch.
Sounds good to me. Okay, so Yazenga asked Ben, what's the recommended size of the lightning rod?
Yeah, so I think in the construction manual, it's a construction issue, the rod. So maybe, I don't know if Moti can answer it, or we can check the construction manual and follow the plans.
I think it's 40 millimeters by 10, if I need to gamble, but I'm not sure 100%.
Sorry, the question is about the reinforcement bar?
No, the rod that goes down to it, that connects the bus bar to the earthing.
The width,
it's a galvanized steel.
The width is 40 millimeter, the thickness is 10 or 12 millimeter, and the length is about 1 meter to be able to stick out of the ground slab. And the material should be galvanized iron to allow the right resistivity and electrical properties. And in some cases where we couldn't find this specific material, we allowed an alternative of zinc coating.
Thank you, Moti.
Thanks, Moti. Thank you, Ben. Thank you, Meir. This has been very productive. Have we wrapped up water? I think we've wrapped up water. It only took a day and a half.
Good, excellent. Okay, so according to the schedule, we are supposed to come back at 2 o'clock.